No. Okay, now they should be able to hear us. Right? Okay. Thank you guys. That sorry we're a little late because it was the first time we started running this hybrid mode. You know, this is not just local. We have more people online than we people here. So good morning, everybody. Welcome to our UT Mobility Forum. My name is Visual-Inertial, a professor of chair of Department of Computer and Information Sciences. And before we starting today's slide and introduce our speaker, I want to give you a little background about the UT Mobility Forum. So what happened at the University of Delaware is we have a pretty large group of faculty and students are very actively working on a variety of topics related to the mobility. So ranging from electrical vehicle, battery technology, and alternate energy. Obviously, we have people connected, autonomous driving, robotics, and transportation, smart infrastructure. Even we have people on the policy, you know, on how, you know, what's the policy can impact for the people with disabilities and etc. So this is the very exciting things. Because of that, we decided to running this monthly a UD Mobility Forum. So the forum serves two purposes. One is for the internal people, so that we get to know each other, and then we can stimulate the collaboration, you know, within the university. At the same time, we also want to, you know, build a partnership and you know, collaboration with our external people. I know today we have several you know, audience come from several companies, including Toro Robotics, which is one of these a startup the startup that belongs to Daimler group. So there is quite a few, you know, industry folks are very interesting to see what we are doing here. So I think welcome those of you on the Zoom. I know it's kind of interesting. You talk to the people on the Zoom. I think that's the basic idea. And starting in January, we started this UD Mobility Forum. Today is my great pleasure to introduce our first speaker, inaugural speaker. So it's Dr. Paul Huang from Mechanical Engineering from UD. So Paul is a rising star. Actually, I should say it's a real star in the area of robotics and particularly on the UAV, you know, navigation and the system. So Paul got his PhD from University of Minnesota in 2012, and before he joined the UD as a senior professor in 2014, he spent 2 years at MIT as a postdoc working on marine robotics. So he has been very successful in right now in serving both academically and industry. So academia, he right now has been serving associate editor for several top, you know, transactions in the robotics, including transactional robotics and robotics automation and lasers and etc. And then besides that, you know, he's also very active, you know, leading some industry efforts in terms of the robotics. For example, he has been, I think he's still on the consulting role right now as a principal scientist at the Meituan Group. So for those of you who don't know Meituan, he probably will introduce that later. So Meituan is the largest food delivery company on this planet. Oh, sorry about that. It's still under the construction, building still new. So I think he's gonna share with us a lot of very interesting observations, which our academia normally you never see them. So I think without further ado, I will give the podium to Dr. Huang.
Thank you. Thanks, Wisdom, for very kind introduction. I'm very happy to be the first speaker over here for this mobility forum. So yes, today I'm primarily talking about recent research results from my group here at UD, but I will touch upon some applications from industry. So just sorry. Okay, so to begin with, Meituan. Yes, I'm in the last 2+ years, I'm on sabbatical working on Meituan. I'm primarily focusing on delivery, autonomous delivery. And here's one example showing using drones for food delivery. And basically, you can see this shows the the basic steps of the whole system. Of course, two ends. We still need the delivery boy to pick up the order from the restaurant, and then still using human to upload or to mount it on the vehicles, and the vehicle then will fly to the user's end, and the landing we call airport. And once it's landed, it will text message to the users and say, your order is here, you can come up to pick up from the station. Okay, so that's basically the whole process. And of course, it's a very complex system. We really want to build a low altitude logistic network in a city. Okay, and we, in the last 2 years, we do achieve quite some milestones. And here just one, and actually we just released the stats last week. So in 2022, we delivered actual orders over 100,000 orders to the actual users, and which is basically 4 or 5 times than what we did year before in 2021. So with actual orders, and we basically, this is again, it's not a commercial operation. It's still we cannot collect basically revenues because it's still like operation trials, but it is true actual orders. We're using drones to deliver the actual food orders to the users, and we want to build basically use 15 minutes delivery time, cover 3-kilometer area. So basically we want to build a network, logistic network for 3 minutes, 3 kilometer radius, 15 minutes delivery, faster delivery for the users. And we have a lot. We so far we basically we have flights for over almost like 500,000 flights, including testing flights. And we this year, 2023, we will operate in. Last year we primarily operated in Shenzhen, and this year we'll also start normal operations in Shanghai. So these are basically, I think it's in the last 2 years. Of course, I contributed a little, but it's really the group efforts from the company, from Meta. But I'm using this as just a motivating example for my own research here at UD. So here's the talk about today's talk, really about the visual-inertial systems. Because really is because this is one of the building blocks for the whole system, and I'm very proud to say that this technology has helped a lot for drone delivery and also the other applications I'm working together with the industry program, in particular the metaverse, like the AR, VR, the augmented reality and virtual reality. We have been working very closely with Google and Facebook and Apple. So to begin with, what's a visual-inertial system? So visual-inertial system is really a combination of 2 types of sensors, which is inertial sensor, inertial measurement unit, and then the cameras, right? The visual and inertial. So why these 2 sensors are interesting? Because they are actually very, very complementary and can provide a very interesting data information for all kinds of autonomous systems. And for example, the inertial sensor can provide very high rate 6-DoF motion information with a scale. The scale, I want to emphasize scale, the metric scale is very important for actual robotics. And but it has it's not nicely or easy to work with, in particular for these cheap low-end MEMS sensors. For example, it is biased. It has it has a lot of noise. It has gravity also coupled with the measurements, and we need to deal with that. And the camera, everyone knows camera is a commonplace now, right? Everyone has a phone, and every phone has a camera, so multiple cameras. And the camera is interesting, and it's very, very useful. It provides very, very rich information about the environments, about its motion, and but single camera, it doesn't provide scale because large objects will appear small if you look at it from distance, or small object could be look at it larger if you close it, right? So it doesn't provide a scale. And it also has, it's a low rate, probably, 30 FPS, 60 FPS, that's the normal frequency we have for the current the cameras, and also heavily depend on lighting, right? Lighting condition, it can significantly affect the images, right? So combine these two sensors, it provides a very interesting way to address some of the perception problems and some of the navigation problems in robotics, in AR, VR, and of course the drones is one example of the robotics. And of course, automotive, I just listed here a few examples. We have the Mars helicopter, which is also flying on Mars, which actually exactly using the technology I'm going to introduce, basically which is called Visual-Inertial odometry, running exact same algorithm we are running on my phones, on my drones, okay? Even on the ground vehicles. And the meta, of course, also the middle is a autonomous vehicle for delivery. And of course, the vehicles, ground vehicles typically also have a lot of cameras, sensors, and of course the other sensors. And then on the right, which is AR, VR, metaverse application, basically, a lot of industry is very, very interesting in this technology, try to build this metaverse or AR, VR technology to enable metaverse applications, right? You have, headsets or phones, and you need to able to track the 6 law of motion of your headset so that you can add some virtual object into the scene, so that the virtual and the real environments can be nicely and accurately mixed together, right? That's basically the fundamental problem. So it's very interesting and also of course hard. So the backbone of this system, to me, of course, different people have different opinion or different take on this. But in my research on visual system, the backbone is the inertial navigation, which is a very classical problem in aerospace, and it's a very classical estimation problem. Really, the inertial sensor provides the local acceleration measurements, and the gyro provides the angular rate measurements, and also some other type of magnetometer or barometer, etc. But how to use these sensor measurements to figure out the motion in 3D, right? That's really inertial navigation problem. And of course, because these days the inertial sensor we have, for example, on my phones is very cheap, like just $1 sensors, and these sensors are cheap and small, cheap, but of course the data quality will be not that great. So we need to figure out, we typically want to leverage the other sensors to help to reduce the drift, or to mitigate some of the challenges inertial navigation faces. So we will typically, for example, in robotics, we're typically using some aiding sensors, including cameras, LiDARs, or GPS. And if we navigate in space, we will typically using the sun sensors or star sensors to aid, to help reduce the accumulated errors of inertial navigation. And this talk today, I'm probably focusing on one very interesting aiding sensor, which is a camera, which leads to the visual inertial navigation, or VINS in short. So really we try to use a camera as an aiding sensor to reduce or to help inertial navigation, because navigation is one of fundamental capability for autonomy, because you have to know your vehicles, your robots, how to move, how to navigate, right? So just a little bit of math behind. So we have two sensors, right? Inertial is the backbone sensor. So what's the model of IMU, inertial sensors? Inertial typically we're talking about a 6-axis IMU, which is essentially has the 3-axis accelerometer and the 3-axis gyro. Accelerometer basically measures the local linear acceleration, and the gyro measures the angular rate, right? And in particular, the accelerometer, which is, in particular, we are talking about near Earth application, the gravity is always a big part of that, right? Because meaning that your accelerometer will measure the linear acceleration, which is 9.8 will be involved. But the 9.8 is always along that particular direction, right? You need to able to get rid of it. So the orientation, the attitude will become a very important part of the problem. So, and these are very classical. The model behind is you can pick up any inertial navigation textbook. You will find the math behind. And so I just listed this ODE here. One takeaway message over here is that these equations are nasty. In particular, the first one and the third one. The first one is about the thermodynamics of your attitude or orientation. The third one is about the velocity. And these kinematic equations is, of course, nonlinear. That's the basic problem I want to, the fact or the observation I want to point out. These equations are not in particular the first one and the third one. Because these equations are nonlinear, so we write this equation in this generic nonlinear function FC. And what quantities, what states, what variables we are interested in. We want to, of course, we want to compute. We call PVQ, which P is a position, V is a velocity, Q is a so-called quaternion, is a slightly the rotation, so basic attitude, right? And the other Q is a bias. Bias is a time varying, which is corrupts the measurement, but it's a time varying. It's something we cannot simply ignore it. It's plays a very important role. If we don't take care carefully, it will be incur troubles. So basically, that's basically 15 states we want to estimate for navigation. So PVQ and two biases. And when we build an actual algorithm to use this sensor, we need, because it's continuous time, we need to transform into discrete time. And for how to do this conversion, integration, simply integrate based on the sampling interval, we integrate these measurements and have this discrete time nonlinear model, which describes the IMU measurements. And this is the model we are using for building navigation algorithms. Okay, so as I said, because we are using the cheap sensors, and the cheap sensors, if you blindly use it, there's a lot of, it's not going to be easy. So a lot of intrinsic parameters we need to take care of. These parameters including, for example, the scale factors, the misalignment between these two sensor gyro and the accelerometer, and also the skewness, etc. And there's like 15 to 18, how do you parameterize this? That's basically dozens of parameters which are very important in order to able to nicely use these sensors. Okay, this is just one thing I want to point out. Another side, camera, right? Camera is a very it's a commonplace, right? And the model we are using is also pretty standard pinhole camera model. Essentially, we project a perspective, project a 3D point on an image plane, which is basically this equation describes this process and the standard again. And for camera, there's also a lot of intrinsic parameters. So we need to take care of, for example, principal point, the focal length, and distortion parameters. If we're using the rolling shutter cameras, the readout time also need to very carefully need to be adjusted. And since the visual inertial two sensor, we need to combine these two sensors. It's a sensor fusion, right? So the extrinsic parameters between these two sensors are also very important, which includes the spatial and the temporal calibration. The spatial meaning the rigid connection, rigid body transformation between these two sensors, and the time offsets between these two sensors, if the sensors platform are not hardware synchronized, right? So all these parameters, a lot of things are going on in order really to build a system which can work nicely. So the visual-inertial navigation of VINS is really, as I said, it's a sensor fusion problem. And if we don't have any constraints, meaning that if we don't have computation constraints, if we don't have memory constraints, if we don't have any communication bandwidth constraints, the problem is solved to some degree, which means I can build a very large nonlinear discrete problem or optimization problem to solve it, right? I just click a bunch of data measurements and transform into formulated into this optimization problem. We have very nice solver to solve this kind of optimization problem. But the problem is for a real system, we have a lot of constraints. We don't have that much computation, right? If I fly on or if I run on my phones, I've got my phone computer actually pretty nice, pretty good these days. But we do have because essentially running on embedded systems, we have a lot of computation constraints. And that's one example. So, and if you look at the problem formulation over here, you can imagine if my K is a timing, right? If my system running longer, the N becomes larger, and for cameras, also probably we'll see many feature points, right? These are basically dots, feature point, as also will grow. So the problem itself is it's kind of unbounded as time goes, right? So it eventually will become computationally prohibitive. So how to address this problem? And in literature, people typically decouple or partition or decouple the problem into multiple subproblems. One is running a very fast so-called tracking system or odometry system, which is a visual-inertial odometry, and which is essentially, I only care about recent images, recent data, and try to quickly figure out my motion quickly. So of course, it will accumulate errors quickly. So, but it's fast. So to address those problems, then we are running another problem in the back end, which is optimization problem, and using the past data, running relatively larger optimization problem, try to get a better results, and which is back end. And of course, it's more accurate, but it's more expensive because the problem size will grow. And another, where how to combine or how do I benefit front end, benefit from the back end. And typically people assume the back end results are perfect, are true, which is very large, very strong assumption, because no matter computation, no matter optimization you solve, the results always has some inaccuracy, right? If that not taken into account when you're using the result, this will can lead to we call inconsistency. So in the last several years, my group intensively work on this problem, try to address some of these problems from and back end and so-called loop closures or relocalization, and try to improve, try to advance the state of art. So the backbone algorithm, one of the very popular algorithms is so-called MSK. Really, the idea is that if anyone has worked with cameras, one of the problems of working with vision is we can see a lot of features, right? If we cannot maintain these features in real time in many cases, right? Somehow we want to, address this problem without sacrifice too much computations. And the key idea of this approach is that, okay, I don't maintain these features in my optimization variables or not in my state vector, but I still want to use these feature measurements, right? So how to do that? Really, I have a drone flying over, I see a bunch of green feature points, the star showing over here. And of course, if the green stars grows, these blue measurements will become more and more, and eventually there becomes too many you cannot handle, you cannot process over real time, right? So the idea is that somehow I want to transform these blue measurements into red ones. The red ones is only constrain the camera motion. The camera motion, which is very well bounded in terms of size, right? So that's really the key idea. So because blue ones can grow quickly over time, but the red ones, basically I want to convert or transform these blue ones into red ones. That's really the key idea, the key problem that MSK want to address. So how to do that? Of course, I maintain the math. I don't want to go into details, but the key idea is that I can maintain a bunch of so-called camera, the past history, a short period of time of the history of the camera poses. This is so-called clones, and we want to maintain these camera poses in the past, and I want to use this to process these blue measurements, transform these blue measurements into red ones. And the process, leveraging the common filter, which is a propagation. I have an IMU kinematics, I can propagate with this. And because I want to maintain a short period of time of the camera motion, I need to clone, I basically augment the state a little bit. And the feature trackers, the features can categorize into 3 different type of features, and I want to use these features for update. For update, because these features are not, these green stars are not in the state vector. How can I use the corresponding measurements? So the key idea here is a so-called non-space projection. So basically project these blue measurements onto the states involved, the camera poses only, the drones locations only, and this is so-called also so-called linear marginalization. By processing this, then I create a new measurement which do not depend on the features. Then I can using this new measurement to update my states without worrying about the features anymore. That's really the key idea. So my group has basically building this key technology around and build a lot of different algorithms. One of them, which is basically so that the foundation in the past for my group, which is OpenVINS, we also open source. Basically, it's really kind of platform for visual-inertial systems. And actually attracted quite a lot of attention in the last 2 years. And some the industry also, has tried to use this technology running on actual robots, etc. And a few key features of this system, of course, we try to make this system as easy to use as possible, which means user-friendly. The end users don't need to worry too much about the math behind. So it's built upon based on the type-based state management. And also we include a lot of, which is important, the calibrations. We include all sorts of calibrations in the system, spatial temporal calibration, including intrinsic, extrinsic. And we also have some the nice treatment how to make the system more consistent with so-called phage. And we also have, because we're running on phones, for example, the initialization, how to initialize systems is very important because it could be happen at the beginning. It also can happen in the middle because we want to reset the system very often. So dynamic static initialization. We also provided quite nice detailed documentation and simulation, and people can easily use it. Some comparison, of course, we can show that it's basically one of the state of art in the community. Built upon this, we, in particular in the metaverse application, AR/VR applications, a lot of plans, right? A structured environment. How can we leverage? How can we utilize this structure information into the system? As this is a very recent work. It's basically trying to leverage the planar regularity from the extracted from the environments to help the visual-inertial automobile VIO. And which you can see because for example, this teapot is a virtual, right? Because that's the AR application where you want to add some virtual objects into the scene, right? But make the scene, make the images realistic, right? Otherwise, no one wants to use it, right? So one of the backbone, one of the key problem behind is how can we accurately estimate or compute the motion of your camera, right? Because when your camera is moving, if you cannot accurately compute the motion of your camera, any object, which object you insert into a scene will be unrealistic. So that's really the downstream, one of the downstream application of this technology. And recently we also reformulated against the front end. This front end motion tracking system is a so-called VIO. But recently we reformulated the problem instead of word-centric into the robot-centric or sensor-centric or ego-centric formulation. The reason is that because most of the time we are care about the motion, the fast, quick, relative motion. This motion, because it's more important, because I don't care too much about a long time ago where I am, but I'm care about my current velocity, my current rotation. So we formulate this robot central formulation, and of course a lot of stuff involved over here. But the key idea is that this load formulation helps us to able to compute relative reasonable motion more accurately, more consistently. And these are results experiments we did. Basically, drive you can recognize it, right? Basically, we put on a car, driving around the campus, and just using a single camera, single IMU, and try to figure out the motion, basically navigating the motion of the vehicle. And open loop, just simply front end VRO, visual-inertial odometry. Of course, it accumulates errors, but the error is this experiment was did like a few years ago, I think in 2019. As that time, we compared to one of the state of art, which is from Google, we call AR Core, which are still collaborating with them these days. Basically, we can beat them at least for this experiment. And as I said, the visual-inertial odometry front end is open loop. It accumulates errors, right? But how can we reduce or mitigate these accumulated errors? One of the technology we need to develop is a loop closure. Basically, how to detect the images or the locations I have visited before. This information is very important because this information can correct my accumulated errors. So, and how to address this loop closure event detection. Of course, we are leveraging the images, and this is also quite a few years ago. We will build a very lightweight UNet-based, essentially, autoencoder based a network can detect these the similar images very fast. And even I look at the image in the daytime. I take an image from in the evening as we can. If they are corresponding to the same physical location, I can still figure out these are the same location I saw before. And then later on, we also integrate the semantics of the environment, because for example, I see a water bottle here. This object is very informative, right? Because this information, because I see another object which is not bottled water, which can help me to help me determine this might be another location I saw before, right? This semantic information also very informative, very important, very useful, and we integrate this information into a network and help us to further improve the performance of loop closure. So once we have this loop closure, how can we use it, right? And loop closure detection I just show essentially just tells me, okay, this is a location I see before, but still didn't provide this the motion constraint yet. So how can we use this loop closure constraints on the motion? Because at this point, I'm care about my navigation, my motion. So again, if we are given infinite resources, the problem is not a problem. I can solve it nicely, just running huge optimization. The problems we don't have that much resources. How can we address this problem in a very relative fashion, quick fashion? And we build a so-called linear complexity algorithm for this problem, try to utilizing loop closure. And the key idea is we using a Schmidt computer Schmidt curve idea, and this is not new stuff. We invented actually. So I think it's invented in the 60s, 70s at JPL. Basically, the idea is that okay, given these set of measurements, I don't want to compute to update this bunch of history of what we call keyframes, the past long trajectory, but I still maintain them. I don't estimate to compute to update those trajectory or these keyframes, but I keep these things in my state data, not update them, but I still utilize the measurements. I still use these measurements to update the
It's okay.
okay. I still want to use these measurements to update the correlations. And without updating, we computing the states of the past history, it basically reduces the complexity of the problem from a quadratic, at least from a quadratic, sometimes a cubic, to the linear. This is really the key, and it turns out very easy to handle. Essentially, just state the corresponding common gain to 0. The implementation is very simple, but it turns out very effective. So here's just the result with the system. We using compare with a loop closure without a loop closure. You can see using loop closure, the trajectory becomes much neat, much more compact. And yes, so just for a second time, I just move on. And recently we also consider multiple sensors, multiple cameras, multiple IMUs. And again, still taking into account these computation resources constraints. Because if we don't have constraints, we can build a huge problem to solve it, no problem at all. But the problem is how we can efficiently solve this problem. The key idea here is essentially, we only maintain the base camera, base IMU, but with this base states of these sensors able to still process or utilize the measurements coming from the other sensors. That's really the key. And the key technology involved over here is essentially this on manifold state interpolation. And it works very nicely. And we built a sensor platform which have 3 cameras, 3 stereos, but we're only using 3 monocular camera and multiple IMU, 2 IMUs. And we can demonstrate the system can run real time. And also one of the nice property of the system that the sensor failures, we can handle sensor failures in a very robust, or we call it resilient way, meaning that if a camera fails, doesn't disturb or interrupt the system at all, as long as I have one camera. So meaning that the sensor fails, my output still will be smooth without any interruption. I think that's the sensor failure and resilience is also one of very interesting and important advantage of the system. So back to the outdoor, right? We do have a GPS in most cases, in particular for vehicles. I think I have a low battery. Anyway, so basically we do want to integrate the GPS into the system. So basically here how to integrate the GPS into the system nicely. The GPS, in particular if we're talking about this single point GPS, like basically the cheap GPS, and sometimes we have it, we don't have it, it's unreliable, right? Sometimes even unavailable. So to address this problem, then the sensor calibration is very important, and also the initialization, meaning that because GPS provides the global absolute position on a global frame of reference, but my camera and my inertial is on its own sensor frame of reference. How to align these 2 frames on the fly when you actually run the system, right? So that's really the 2 problems we tackled in the system, initialization and sensor calibrations online. And it works nice, and you can recognize these are basic experiments we did on campus.
Oh,
yes.
Can I ask you a question? Here, when you run experiment, it's a UAV on the air or is it on the ground?
No, this is a ground vehicle. Basically put on a car, and we collect data and running it. Yeah. Okay. So, and these, sorry, I think I jumped too quick. Yeah, so basically this is just simply integrate that we call intermittent, because sometimes GPS, indoor we don't have GPS, but when we go to outdoor, the GPS becomes available, but probably not that accurate because it typically requires a few seconds. You have a better signals from GPS, right? So how to handle this intermittency in a system, and here we basically build upon that work one step further. Basically, we so-called we integrate or we fuse the raw data, the pseudo range from GPS instead of just XYZ, and we will integrate the pseudo range and face angle, I think not yet, but here we directly fuse the raw data for GPS, in particular, in this case, using fuses the pseudo range from GPS. And here we integrate not the GPS, but the odometry with relay encoders, because when we're working with the ground vehicles, the relay encoders are actually you will have it, right? How to integrate this, how to fuse this or the relay encoder measurement into the system. It sounds it's clearly it's a definitely provides very useful information, and if we don't use it, we definitely will lose information, right? We want to use this in a very nice way. And one of the key challenges here is that the relay encoder provides a 2D motion constraints, but the whole system I'm building over here is for 3D, right? So how can we nicely integrate this 2D motion constraint into 3D? That's one of the challenges we are facing. Of course, all the sensor calibrations we need to take because the different sensors have different frequencies and also they are mounted on the vehicles at different places, right? So this calibration is very important. And so how can we integrate all these different sensors on the vehicles, LiDAR, camera, GPS, and the relay encoders, etc. So this comes to means, and the system we are still building it, but we do have some preliminary results showing that we have a pretty nice, decent system prototype at least, to showing that we are able to real-time fuse all these multimodal sensor information to provide a very accurate motion localization results. Okay, let's simply quickly jump. And another we're looking at the problem is multiple vehicles, right? Here, essentially, we want to build a so-called cooperative distributed cooperative localization among multiple vehicles, multiple cameras. Sometimes you can simply think of that way, because the drones, you can think it's the flying cameras. So how can we build a distributed system to enable multiple vehicles can cooperatively localize each other by leveraging the measurements from different vehicles? And here we're particularly interested in the problem that how can we utilize the measurements from other vehicles which are taken at different times? For example, because I see this water bottle at this time, and next time you see this water bottle at a later time. Clearly, we see the same object before, right? So this definitely provides some constraints, but we see the same stuff from different cameras at different times. How can we leverage, how can we utilize this constraint into a system? That's the basic problem we're solving here. And the key technology behind is the so-called coherent intersection. All right, so let's move on. So from navigation to perception, because perception is very important. One of the things, because a lot of, in particular working with the robots, right? One of how do we perceive the objects in 3D? This is really, really important because you want to make your robot do something, right? How to interact with the environments. In order to enable this interaction, the perception becomes very, very important. And of course, one of the most challenging problems we are facing in autonomous systems. And here we are looking at the object code 6DoF or 3D or 6DoF object tracking. Basically, we are tracking objects, not just a single point. We do care about the volume of objects, right? The pose. So, and here basically, we're using a single camera, single IMU. We have a robot tracking another a vehicle, right? And this vehicle is not a single point. It's really a point cloud based representation of this volume. And we detect these, track these objects online, and also compute the motion of these objects online. And it turns out works pretty good. And another problem we have in particular for single cameras, how can we quickly, nicely, accurately estimate the depth, so-called distance to the object, to obstacles? Because that's really one of the very, very important problem. Because if I want to fly my drones quickly in a very cloudy environment, how to safely navigate? That's of course one of the basic problem, right? But this is not an easy problem. In particular, I want to fly my drones in the forest. I fly like, say, I fly 20 meters per second, it's very 30 meters per second. How quickly find the compute distance to the closest obstacles, that's very, very challenging and also very, very difficult. And here we basically build a network, leverage very fast depth network, and also utilizing the sparse feature, which provides a 3D information, basically provides 3D information, meaning also provide a 3D the sparse depth information. And we leverage this sparse depth into the system to help this depth learning. And we also try to, again, similar problem, we try to build a very, very efficient real-time, the 3D mapping of the system. And again, the challenge here is, again, always the computation resources. And in particular, I want to build a very dense mapping of the environment. The computation involved in general, very, very huge. So we leverage this code idea, meaning that in order to compute this depth map, I using the network, encode the depth map into a very low dimensional code. And this code can be optimized, can be updated in my Visual-Inertial system. And once I have better code, I can review back, basically confirm back to the depth images or depth map. And which depth map basically presents the 3D dense reconstruction or dense mapping of the environment. And but the nice property is it can be real time. And also we are interested in building really large scale 3D map, right? So using the drones flying in the city, I want to build the 3D model of the city, because this is the one of the foundations for the downstream application for navigation, for planning, etc. So the 3D mapping using images and build a large scale is very important, and also of course challenging, because in particular one of the challenges, for example, if my camera looking at a lake, a water, right, lake, I cannot, in general, the state-of-art approach cannot build this surface, essentially, the water surface, the lake surface, because the camera is the textureless, right? So we leverage the so-called these days very popular approach with the nerve, and we're basically able to learn from data, able to build a very robust, accurate 3D map of the environment. And the last piece of work, also recent piece of work, is we're also interested in building the object map, because if I pick up this water bottle example, sometimes I know this is the water bottle is very important, because this is not, this is not a speaker, right? And to able to understand the semantics of object in environment, also very important, in particular when I want to my robot able to interact with the environment, right? To understand the objects, also very important for these days. And recently we built this SoSlam, which basically really try to build an object-based slam. And some of the preliminary showing that we are able to build this system in real time, build this object map in real time, and or even facing some very challenging objects. So here we primarily focus on the symmetric object, because a ball, right, is symmetric. How to, if I look at it from different angles, how can we still able to reliably build this, map this object? Sometimes it's very challenging. Okay, with that, I think it comes to my last slide summary. So my research group really focusing on the from a control, from a system perspective, it's really focusing on state estimation. What I'm talking about, I'll try to compute all these different variables. In the end, it's really how to estimate the states. So state estimation, and in robotics, we are focusing on the spatial perception in primary. Try to enable the robots, mobile robots or mobile devices to able to understand the environments. Okay, from a motion perspective, from the sea understanding perspective. And there's a few directions or projects we are working on. And all the videos, all most of the source code, the code bases are available at the GitHub, and the videos can be seen at my group's YouTube channel. And with this, thank you. And I think I should say Happy Chinese New Year, right? In particular for the people online.
We have a very cool hour here, so this one is there, everybody can see each other. Even 160 degrees is running there. So I think we still have some time, the goal for this is really open up for more discussion. So both the questions online. If it's an online questions, maybe you can read them. Okay, even there are questions.
Chat.
Yeah, we can take your questions from the audience. Okay.
Yeah, so first, thanks for your talk, which is very interesting and funny. So the first question I have is, how do you compare this kind of like camera virtual based SNAP with the LiDAR based SNAP in terms of the level of accuracy and also the reliability?
Good question. And actually this people always asking like visual LiDAR. My take on this, the LiDAR, in particular for geometric localization or navigation, LiDAR will be more accurate, more. I will actually be very careful because a lot of people online, and in particular in the industry, because that's going to affect the strategy.
Professor. Whatever you want. Don't worry.
So if LiDAR in general is more reliable, more robust than the vision solution. Here I'm talking about geometric localization, geometric motion estimation. I care about the geometric look. I care about my XYZ look GL, right? These sorts of things, these are geometric. LiDAR more robust and in general almost also more accurate. Okay. Given the LiDAR, the measurements are good, right? Because LiDAR still the measurements are based on the reflection, right? Depends on what kind of material the LiDAR is hitting to, right? It's a hitting the glass, I guess, the way you able to handle it. So given the good measurements, LiDAR is more accurate, more reliable, but LiDAR is not always possible. Okay, LiDAR, of course, the LiDAR technology is still emerging, right? A lot of companies are working on this, and becomes cheaper, becomes smaller, etc. Right? And but it's still expensive and bulky, and power consumption is also much higher than camera, and which make these things are not, at least at this point, not always possible. For example, for drones, not possible. Power consumption, size, cost make the LiDAR is impossible. I won't say impossible, but it's harder to scale up applications. That's and that's for geometry navigation, right? Then come to the 3D perception. The LiDAR essentially just provides the points, right? In general, this LiDAR still compared to camera, the 4K, 8K camera images, LiDAR point cloud still sparse. In particular, if hitting the long distance, right? It is still sparse LiDAR point and point clouds. And another disadvantages of the LiDAR measurement doesn't provide that much semantic or rich information as a camera does, right? Because for image, I can easily to do perceptions much easier for images, segmentation, detection, recognition, right? Capture the LiDAR point cloud although people are working on that, it's not say not impossible, but much harder than images. That's my take.
Thank you. So another question is for the work on distributed cooperative brains. Are there drones, multiple drones to do the same map? So are they with the same camera or different camera?
Different camera. So basically, the scenario we are looking at is multiple drones With flying cameras, right? Let's say camera has the idea. Flying cameras flying in the same area, but they are not see the same object, same area all the time, right? Say I have my camera see this table yesterday. Your camera flying in this area today, right? Clearly, forget about the temporal difference. Also, you see the same this table from different angle, although we see the same table. Clearly, we see the same thing, although over different spatial locations, over different times. Clearly, there's a connection, right? At least we see the same thing. So, but how can we use this constraint into system? That's basically very challenging. But it's a different camera, see the same things from different time, from different cameras, and how to enable the system, build this distribution. Clearly, I cannot, of course, if possible, I can store all the data and process in the end, right? But you don't want to do that. You want to build a real-time distribution system because you don't have my information, right? The only connection you have is, suppose we see the same object from different angle, from different time. How can we integrate or at least utilize this information? That's basically the system. I just showed my system. I feel this is some communication, by the way. It has to have some communication, but I want to minimize the communication bandwidth as well.
Let's take a question from Detroit. I know the first one is from Detroit. The next one is from China. So go ahead.
Okay, so here, the first question is from from Wednesday.
Yeah, my PhD student.
Yeah, he has a question about the computation limits, such as the processing time and the memory of the Linux system. So which function of the system are causing those limits?
Talking about the VINS, right?
Yeah.
Okay. Computation, if you look at, depends on which system you're talking about. If I just pick out the OpenVINS, right, that's a basic foundation for my work. OpenVINS, which you basically building upon using this MSK, is one of the popular approaches using in industry, in academia, and coming from my former PhD group. So the computation, intense computation operation coming from the a few places. One is we call measurement compression because we have all these measurements, right? Depends, you say, well, my window is 10 frames, and each frame are tracking 100 features, right? Clearly, these are, if you simply add up, you have 10,000 measurements, right? You need to process, right? So how come, although we will do this non-space projection, etc., we still it's a huge constraint. So we will do this measurement compression, basically performing QR decomposition. This is a very expensive, relatively unique system. Okay, that's one. Another is updates. Essentially, once I do this constraint doing decay update, you generate a quadratic operation, and that's also basically the computation operations which are relatively expensive. At least we can. I want to emphasize it's relative, right? Because the whole system can run faster than real time, meaning that I have 30 FPS, I can process data in 20 milliseconds, 30 milliseconds, so faster than real time. And also depending on what compute platform you're using, right? It's running on my laptop or running on your phone or running on TX2 or some embedded computers, another different story, right? Another thing I didn't touch upon is the front end, visual feature tracking. That's expensive, meaning that given images, you need to detect these features and track these features over frames, right? Over images. That's also at least very expensive, relatively, actually, that's could be the most expensive single operation module in a system, but that can be handled in GPU or in different, or even in a DSP, etc. So meaning that not necessarily running on CPU. Okay, so you say you have different computers, different heterogeneous computers, you have different computing platforms, you can distribute the computation on different platforms. That's what the typical doing in practice. What's the other, the memory? Memory, in the whole system memory is becoming to store the covariance matrix. Okay, covariance matrix is a square matrix, and which describes the uncertainty of the quality of your results. And it's a square. Square meaning that the depends on number of the states. Say I maintain 10 frames, and each frame at least 6 variables, x, y, z will show 60, and the current, say, because I have 50 states, so roughly 100, right? A few hundred by a few hundred. That's probably the largest memory block I need in order to carry out the operations, computations. Okay, that's the memory and the computation.
That's pretty cool. Now people talk about how to reduce the cost. Eventually the cost is memory size.
Yeah, I mean, in particular for the actual application, always boils down to cost. Okay, each single computation, each single operation, I can associate $1 to that. That's the bottom line.
Yeah.
So I mean, for example, if evenly I have a computation power, but the power consumption itself carries the energy. Energy is a cost. Okay, that's
Thanks. We have another question from Zhiliu at YNU. University. Thanks for the excellent talk. I have one question for you. How do you usually obtain the ground truth trajectory pulses for your real world experiment? Ground truth. For example, I want to do the experiments on my self-built indoor robot to test the odometer performance of my SLAM algorithms. However, I'm not sure how can I obtain the GT trajectory for the experiment.
I mean, it's a very practical question, right? I mean, whenever we build an algorithm, how we evaluate, right? What's a benchmark we compare with, and in this case, the ground truth, right? And different ways. For indoor, of course, we typically have a motion capture system, right? Provide the ground truth. If you don't, then what people take, or at least 15 years ago, what we did when I did my PhD, we don't have motion capture system, and we run so-called offline batch optimization algorithm. Basically, that's the best result I can achieve, regardless of computation, right? So I compare to that. So although it's not ground truth, but that's the best I can achieve in practice, right? I run this batch offline optimization, and what the result I get, then I compare my online real-time system to again that. So that's I can imagine the two. Well, of course, if you have the motion capture system provide ground truth, that's the standard way. In industry, in academia, in research lab, that's what we typically do. Otherwise, yeah, against the batch results. Yeah.
I have a question. Yes. Your talk is very interesting, and I'm wondering, in the earlier slides, there is you transform the blue lines to right lines, and to cut down some state maintenance.
Yes.
And I was wondering, once you project the new features in the new frame in the right lines, so how do you solve the feature drifts if your motion estimations have some noise?
Good observation. There's some assumptions behind. Okay, so you touch upon point. If I do this so-called projection, non-space projection, I need to know where my feature is, right?
Yeah.
So if the feature location is inaccurate, first of all, definitely there will be inaccurate because it has errors, right? Because we don't have ground truth. So there's a side module, which is a basic feature triangulation. Basically, the assumption for feature triangulation, or basically try to figure out computer feature locations, we assume the relative 10 frames or 20 frames, the kind of motion are accurate. Assumption, big assumption. If the kind of motion are very accurate, the feature gonna be very, very wrong, and the whole system gonna be basically collapse. Simply. So given the motion, then I try to triangulate, try to localize computer features, 3D, XYZ positions, right? So meaning that for this process, intuitive very simple, given two cameras, right? A stereo, right? I see this point on my bottom order and here, and move, see this again, I can triangulate. It's a triangulation, right? I can triangulate. If I see this more, then I can build a optimization, try to achieve the best result. But here the assumption still, I assume my motion is accurate. This is a big assumption. This in practice system, this motion coming from IMU, coming from inertial. Of course, inertial is noisy. The motion definitely inaccurate, right? But here's it's a trade-off, right? Yeah.
Thank you.
Question, yeah. I have one question.
Go ahead, now it's yours.
Thank you for the interesting talk. I can see how your research address many practical challenges. I'm a cybersecurity person, so I have one cybersecurity questions. When you do the autonomous navigation for the drones, we rely on the sensors or cameras or GPS. All of those are well known for they are vulnerable to attacks. For example, you can do the sensor spoofing attack, the attack sensor. You can create adversary examples to treat the cameras. So those are quite popular and hot topics in the cybersecurity community. I can see it's quite difficult to launch an attack against a drone when drone is flying. But I see when the drone is landing, it's probably quite easy to launch an attack against the drone. My question is the industry interested in this kind of investigation, or they actually don't care about it? And what is the current status from your experience?
That's
Okay.
very good.
Of course, they are very important. They are very open, and industry very interested in this question, in solving this problem, right? And you mentioned the GPS spoofing, right? That's a practical, very, very practical. Even in drones, right? In particular, no one, we leverage the GPS a lot, right? And in my system, we leverage it more on board sensors, which is camera, the vision. But the other drones, right? Many drones in a space, in a place, right? They are primarily leveraging the GNSS, basically GPS, which is satellite, the global satellite-based navigation system, which can easily, not necessarily spoof, but can be easily blocked. I mean, I can simply just, and which happen in practice. I think one of the event accident happened in China last year. Basically, there was a drone light show and a collapse. And again, the people just kind of rumor, right? Very likely because people block the GPS or at least affect the GPS. And in that case, it's not a single point GPS, it's an RTK GPS, very accurate, 2 to 5 centimeter accuracy. I can simply affect, like affect all these signals, essentially electromagnetic signals, right? I can, put a very the high power transmitter, I can easily affect those. So that's for GPS, a very classical problem in the military applications, like many people work on that. And for the other sensors, so for cameras, lidars, this reminds, I think my first NSF project is about the how to secure the navigation for and one of the point we're looking at, so as you said, right, I can easily hack if I'm able to, say the communication channel is opens up or Wi-Fi channel, I can hack the Wi-Fi channel. I can, a simple example, right? AR, kind of a bad or evil application for AR. I can insert virtual objects into the images, and the drones and robots get these AR affected images. I have no idea, right? It's a very realistic that of course your AR is already very, very nice, very, very accurate. I can simply hack it, and people can show. I think 3, 4, 5 years ago, there's an RGB spectrum showing for LiDAR. The LiDAR point cloud, right? People can easily insert some virtual points in the point cloud and basically create some ghost objects, right? And of course, there is another basic kind of hack the perception system. And yeah, industry, because it's really the application is it's not to reach that point, right? We know this point, this question, this problem is important, but there are even more urgent, demanding problem we need to address first. But downstream, down the road, I think it's very important problem. Yeah.
Any more questions from the audience? Online?
Hello, Professor. I still
Yes.
have a question. Is the sound clear?
Yeah, yes, I can hear you clearly. Go ahead.
Great. So I want to ask a question about the camera you select for the drones. So I noticed that you select the camera using the rolling shutter, which will bring some motion blur. I think it's a quite a serious problem for the drones that can move very fast. So first, I wonder why you choose the rolling shutter camera. And the second question is, in what kind of state can the motion blur has limited negative impact?
Okay. Rolling shutter camera, right? Versus a global shutter camera. Rolling shutter camera, I think, is a common choice for actual applications for a few reasons. One is the sensor size much smaller and much cheaper, and also more reliable or robust to the lighting conditions. I mean, for example, if you go from indoor to outdoor and the lighting, the sun lights change a lot for a global shot because it creates images all at once, right? So you can easily get this basic kind of I forgot that name, but you can basically, if you're basically like facing a sun, your image will be very overexposed, right? So the rolling shutter sensors cameras will be more reliable for that because it generates images row by row, right? So and also sensor size is much smaller, and also from the manufacturer point of view, I think it's also cheaper, smaller, and yeah, I think from cost point of view also has a good advantages. So talking about the motion blur and motion blur, I think these days the cameras are pretty good in general in terms of motion. Of course, we always have motion blurs. And rolling shutter camera versus a global shutter camera, I won't say that rolling shutter camera is more sensitive to the motion blurs. Actually, on the other hand, I think rolling shutter camera the images will be kind of skewed because of the images is framed row by row, but that can be handled. That can be adjusted by doing this calibration, etc. I don't think the motion blur is it's not. This is not the biggest challenges for. I mean, it definitely for any cameras you will depends on your motion. You will have a blur issues, but I don't think that's the top challenges we're facing. If you're given blur images, I don't know what else you can do. Not much, I guess, unless you leverage dedicated approaches. But back to IS and the GS cameras, I won't argue that blur for the range shot camera is worse than global shot. I think it's I won't say that it's significant issues, but compare rolling shot and global shot in terms of from the blur point of view. Yeah, but the rolling shot cameras have some great advantages in particular for real applications from a sensor point of view. Okay.
Great, thank you, Professor. You calmed my worries.
Okay, probably not.
So we can take one more question.
Yeah, so
No question from this.
I have a very general question about the drones energy efficiency, because basically the drones are automotive and cameras and the computation may powered by the same battery. So I'm curious how the breakdown of these different components and if that's also a big issue for the operation of drones.
Power consumption, so it's in particular for embedded system. Drones is one, and even for phones, right? For example, for drones, we typically for each single sensor or computer electronic components. I just talking about the drones that I have been working on. Like the power consumption cannot go beyond 12 watts. 12 watts is basically kind of the upper limit, because the whole electronics on the drone probably about 30, less than 40 watts. So you can imagine why the LiDAR has trouble going to this, go into this embedded vehicle systems, because at least the power consumption for LiDAR easily can go over like 30 watts, and I don't know we can some can go down to 15, but that's for the DJI light box. I think it's can be roughly 15 watts. But in general, that's a power consumption, because if you look at the drones, the battery technology is always one of the bottleneck for these mobile devices or mobile vehicles. It's really the battery technology. I don't know if you look. There's always can break down the cost. For drones, actually, major cost is from the battery. Battery essentially come to the energy, right? Come to the power. If you give a fully charged battery, if you can use more, use longer, the cost will come down. So that's why the power consumption for each electronics, essentially the drones is aviation electronics, right? So the whole system has to be very power efficient, energy efficient, otherwise can easily drain the power, the battery quickly, and that can incur a lot of cost. And in particular, in maintain scenario, If we want to scale up, that's huge cost. Right.
Paul, I have a question. When you're running this 400 stuff at every car, do you have in a room sitting here so you can watch every single, and how do you manage this 400?
Only,
This is just fleet.
oh yeah, well, we do have, we have a very, for drones, yes, we have with cloud, essentially the remote. Yeah, basically, because- You mean the drones?
Yeah, drones, we have a human here to watching.
Yes, we do, and everyone, because that's why it's a remote control, right? Because definitely some drone will go wrong, right?
Yeah.
You should be able, because we are not building consumer drones, right? This is a commercial operation in the airspace, right? And in US, anywhere. It's a very regulated area, which means in stages such as FAA, which requires you have to kind of heartbeat. Basically, you need every single time you need to able to monitor your vehicle, although you do not necessarily to interfere the vehicle operation, but you need to able to take up control if it's needed.
Okay.
So yeah. So that's why there's another cost, the human cost is also a big part of cost. Basically, we try to reduce the vehicle human ratio. Basically, one human in a remote, how many vehicles it can monitor, right? So we're targeting basically actually in the drone space or area UAV space, it's also like very similar to the autonomous driving. We have autonomous driving, level 1, level 2, level 3, level 5, right? The drones, FAA also has a similar category essentially, but not the 5 levels, but the 3 levels. Level 1, level 2, level 3 is really based on the vehicle human ratio. That's basically, if I pick one single metric, that's the metrics. For example, going to level 3, I think FAA is looking at 20, basically one human can monitor 20 vehicles. Hello? Yes. Yeah, that's
1 person, 20.
yeah,
That's level
yes,
1.
yes, but 20, it's still, if you look at that's FAA, so they call AFR, so automated flight levels. So basically how the autonomy of your system essentially. They are using this basically AFR1, AFR2, and AFR3, and 3 is basically 20. Basically, one human can handle 20 vehicles in remote at minimum. Of course, but level 4, that's level 4. Level 4 is basically no human, right? Infinite, this number. But that's kind of holy grail. It's very hard to achieve. But yes, but in order to make the operation to be sustainable, 20 definitely is not. It's not a target number. If you have 20, I don't think this whole system, at least in my brand, the system cannot be sustainable. Meaning that it's still losing money.
Yeah, a lot of humans.
Yes. So.
Yeah, I think I want to have a follow because Neil is here. I don't know, Neil, do you want to introduce yourself so people know who you are?
I'm the director of transportation department.
So if you guys have any parking problems, public transportation problems, here is the boss. Okay. And then Tracy, some of you probably know. Tracy, do you want to?
Yeah,
Just very briefly.
yeah, I'm Tracy Schickel. I lead corporate engagement for the university, and a lot of my responsibility is developing the partnerships on STAR campus and the rest of UD's campuses, and to help support faculty if they wish to engage with corporations to support their research or student success.
Thank you so much.
Thank you.
This building, basically, even while Tracy will help us. We have transportation, how to get it here. Then we have people who take care of beauty, and we are all set. Actually, I'm thinking about, Tracy, think about this. I think a pose idea here is, when we talk about students moving to this campus, right now, the first question when I talk to faculty is asking, how's the transportation? How can I get to the main campus? It's small here. Second question is, how can I get the food, right? So that's a big issue. So how about the university thinking about using some of these drones that we can partner with a couple of restaurants on the main street. So during the lunchtime, so that we can sort of order and let them just fly land in the modular lab, because the POS lab, my lab, we are all in a modular lab here. The Rosalie can also take advantage of that. So we can have some drones to fly the food here. Because this is really cool. It's sort of a real problem. Because right now here is so many people moving here. So when they, it is kind of a waste of time. But in this green area, it could be a very nice drone parking place. So Paul, I think this is good. Maybe
Good idea.
we should starting sort of a sponsor a little like one project, so the people at least can partner with one of the restaurants, so they can sort of deliver food here.
Let's organize a meeting and talk about a pilot.
Yeah.
Yeah.
Pilot or something like that. You see, the technology is already here. They can fly in Shenzhen. I'm sure the flying in Newark is okay, right? But that would be pretty cool. I saw a lot of people to delivery in nationwide in some campers. So they are right now is on the ground. On the UAV deliver food. And I have
More probable is still from ground vehicles, I think, because, okay. Airspace is a very regulated space, meaning that a lot of regulations has to be involved. Otherwise, it's almost, different countries have different regulations, and in states actually not. That's why Google Wing and Wing is a basic Google Alphabet company working on the exact same problem as Meta, basically using drones for delivery, and Amazon is working on that, or Walmart is working on that. So the Wing is primary. They have some pilot operations in Virginia, and I think it's coming up with operation in Texas, I think in Dallas. But their primary operation is in Australia. Okay, there's some reason behind, because regulations, different countries have different regulations, and you have to push forward that regulation. Every country is actually working on this, and China, Japan, Korea, Europe, and the States as well. But it does not for drone delivery or drone operations. It's not sometimes not simply technology barrier. It's actually a lot more. But for ground vehicles using autonomous driving, I think we may have to also work on that. On campus, I think that might be a very good pilot project for just kind of, because essentially on campus, it's for these regulation barriers, I think much easier to deal with as a university, where we're doing research, or we're doing and also using the actual application to drive the research, right? So I think that might be a good starting point.
So Albert was here from our government relations team, and he supports these types of efforts that are pilot, where we need the government to support this by way of policy and regulation. So we can pull in the government relations team as well.
Good.
Yeah.
Because I remember several years ago when we have drones, at that time, then try to register vehicles, try to fly the vehicle on campus. Still need to, there's some paperwork or some.
One of our colleagues in the real estate office is a certified drone operator, and he drones Star Campus nearly every day to monitor progress on our development projects. So there are mechanisms we can pull in to talk about a pilot.
Yeah, Tracy would do, right? Because if we want to do on the UAV, drone delivery. On the ground case, in our lab, we have developed a food, that one can be separately can be used. You already have a box here, but I doubt you can safely riding from the main street to here. So we will talk about this later, but that might be something we can piggyback on our UD bus. Right, but anyway, bus it must miss on the food loop there, so if the food is automatically piggyback, and then it can ship it here, that might be also, anyway, yeah. I think we are run out of 4 minutes over, but we starting with 4 minutes later, 4 minutes. Let's thank our speaker one more time. So thank you all for coming, particularly people online, so thank you for being here. If you are from China, and it's already last day of this tiger year, right? Today is the last day of the tiger year in China, and then tomorrow will be the new year, right? Happy New Year.
Happy New Year.
Bye. So, thank you. Yeah. Thanks.
Every year is good year. So with this rabbit year.
Yeah, I am. Okay.
I'm gonna look.
Okay, here it is. Let me show you that.
I only know.
I have a
I'm dragging.
Dragon.
Yeah.
Oh,
Yeah.